Welcome. In this video, we're going to go over another optimization problem, and we're going to use a 6-step process for solving this optimization problem. A box with an open top is to be constructed from a square piece of cardboard 3 feet wide by cutting out a square from each of the 4 corners and bending up at the sides. Find the largest volume that such a box can have. Those of you in my Canvas course should be laughing at the joke in the Learning Objectives page by now. So step 1, let's go ahead and make our sketch and use that to find our objective and constraint functions. And as you can see, here is our sheet of cardboard 3 feet wide, and it's a square, so the length is the same as the width, and we've gone ahead and marked out the 4 corners that will be cut out. And we don't know what amount will be cut out, so I just labeled it X. And the blue dashes indicate that all of these are equal, and they're all equal X. That makes this interior distance, that's this distance here. That makes it 3 minus 2x. Now, what is this box going to look like once it's folded up? It should look like this. Where this is x, and here I have 3 minus 2x, and then here I also have 3 minus 2x. This will be a great start to find our objective, and our objective is to maximize volume, and volume is given in by length times width, in any case, times height. So volume is given by length times width times height. And the constraint, which we can see from this sketch especially, is that the length is equal to the width. So that is the length equals the width equals 3 minus 2x, and the height equals x. Now we can move on to step 2, in which I use this constraint here in the objective function. So our volume is equal to 3 minus 2x times 3 minus 2x, so this will be squared, times x. This is certainly a function of x, so let's make that very obvious here. Now for step 3, we want to find the critical values of our new objective function, so v prime of x. Now before I move on to step 3, let's go ahead and simplify this a bit more. This is 4x cubed minus 12x squared plus 9x. And you'll see why I did that, because in step 3, we need to find the critical values of this, and to do so, we need to take a derivative, and this is a much easier derivative than using the product and the chain rule for this. So we have v prime of x is equal to 12x squared minus 24x plus 9, which simplifies to 3 times 4x squared minus 8x plus 3. V prime of x is equal to 0 when 2x minus 3 times 2x minus 1 is equal to 0, as this interior portion, and actually I forgot to multiply by 3, there we are, this factors to this. So this tells me I have 2 critical values, and one of them is x equals 3/2, the other is x equals 1/2. All that is left is to determine which critical value makes sense and which one does not. So we want the largest possible volume, so we want a maximum. So let's figure out which of these is a maximum. And of course, only one of them will be, since here our volume function is a 3rd degree polynomial, and the leading coefficient is positive. So it's going to look something like this, which means we'll have one max and one min. And we're looking for the one that's a maximum. Maybe you can guess which it is already from that sketch. So as you can see, I went ahead and moved things around to make space. And so let's determine which of these critical values is indeed a max and which is not a max. So here's my number line. 1/2 is here, 3/2 is here. We'd all agree that x equals 0 lives to the left of 1/2, x equals 1 lives between 1/2 and 1 1/2, and x equals 2 lives to the right of 3/2, so that's 1 1/2. Now we need to determine the slope of the first derivative at 0, the slope of the first derivative at 1, and the slope of the first derivative at 2. V prime of 0 is going to equal 9, so this is greater than 0. And I just realized I wrote v prime of 0 here when I meant to write v prime of 1. There we are. V prime of 1 is equal to -3, so this is less than 0. V prime of 2 is equal to 9. So again, this is greater than 0. This tells me that my volume function, that is my objective function, has a positive slope to the left of 1/2, then a negative slope between 1/2 and 3/2, and then over at 3/2 to the right, it goes positive again. So indeed, 1/2 is the maximum, whereas 3/2 is a minimum. So this is the one we want. We want 1/2, the max. And that concludes step 4. I skipped numbering that step, but step 4 is the step in which we confirm that the critical value is a desired max or min, and we kind of combine that with eliminating critical values. And so we determine that 1/2 is the critical value we want to use. Now we are at step 5, in which we use our critical value and our constraint to solve for any other unknowns. We have x equals 1/2, so the length equals the width equals 3 minus 2 times 1/2. And that's just from here. I'm replacing this x here with a 1/2. So this is just length equals width equals 3 minus 1. So the length equals the width equals 2. And then, of course, the height is just equal to x, so the height is equal to 1/2. So the dimensions of this box are 2 feet. So this is 2 feet by 2 feet with a height of 1/2 foot or 6 inches. And now for step 6, and this is the step in where we find, or that is, we answer any follow-up questions. And in this case, it was find the largest volume that such a box can have. So the volume is equal to the length times the width times the height. So we have 2 times 2 times 1/2, and this is feet cubed. Since again, each of these is in feet. So we end up with a volume of 2 feet cubed.